For this next part of igneous rocks, we're going to look at the more felsic rocks on the spectrum. So first we're going to do is bring up our Bowen's reaction series again. And so to understand how these other minerals evolve, we first need to talk about the third mechanism for melting rock. So we've talked about decompression and adding heat, but you could also add water. How does water change melt? So what water does is it lowers the melting point or the solidus of peridotite. And so what you get here is that even though usually places where water is being added to the mantle tend to have a colder geothermal gradient, that is, it's a little bit colder with depth, the depression of the melting point is greater than the depression of the temperature, such that the melting point gets depressed below the temperature at depth quite a bit. And sometimes you can generate substantial volumes of melt using this technique. And so when you do this, you start to, however, the addition of water creates unique chemical reactions that would not happen absent water. And so it tends to favor the melting of very specific minerals that are generally going to be, and the formation of minerals that are going to be higher in silica than your standard, than what you'd find in your basalt or gabbro. And so what you start to see happening is, and so some of the minerals you'll see are things like hornblende, and sodium plagioclase. Just going to put in this box right here above the orthoclase. And so when you start adding these minerals into the mix, you're going to start seeing different kinds of rocks form. And so if you form a rock at depth, the large crystals, these hornblende and plagioclase crystals, are going to grow into a rock called diorite. Diorite, such as diorite and its more small crystal, aphanic form, andesite. And so with ongoing, this is what we call your intermediate magmas. Intermediate lavas, and we're going to refer to them using the blue pen. They contain some mafic minerals. They're sort of somewhere in between. Now, as you add more water, you can also add water to hot rocks in the continents. And sometimes these magma chambers are sort of cool crystallized. The more heavy minerals will fall out, and all that will remain are the lower melting point minerals like quartz, muscovite, and potassium feldspar, and biotite. And so these minerals at the bottom form the basis for your felsic igneous rocks. Your felsic igneous rocks include things such as granite. In fact, you can see some of the and rhyolite. And these are major classes of igneous rocks, the most important ones you're going to remember. There's a lot more of these in your text. This is just the sort of broad, probably 7 most important rocks and the minerals that make them up. But the reality is there's a whole variety of flavors in these igneous rocks. So what I showed you is basically the bare minimum of igneous rocks. However, there's a couple other textures that are important for understanding the larger sort of evolution and more of the story these rocks can tell. One thing we see a lot of in San Diego County are these extraordinarily coarse-grained rocks called pegmatites. Show you a picture. So here's an example of kind of a rather low-grade pegmatite, but what you see, for example, is generally huge crystals, like crystals the size of my thumb. I've seen pegmatites in East County with crystals the size of my head. In fact, just to show you, this is a sliced piece of quartz from a rock I picked up in San Diego, East San Diego County, a couple years back. Now, a couple other textures that are going to be interesting to look at include things like porphyritic. So you notice here, we have some crystals are really tiny, some are large. What you're probably looking at is plagioclase for the large crystals. All the rest of the stuff had a lower cooling temperature. And so what you're seeing in this porphyritic cooling texture is the magma cooled very slowly at a temperature favorable to the growth of this plagioclase, and then cooled more rapidly when it was reaching temperatures closer to the crystallization point of the what I'm going to assume is either hornblende or biotite. So these do not grow anywhere near as big. Now you can also sometimes, in a rock, see something like a xenolith. This is a little piece of whatever that magma was coming up through that got trapped in the magma as it's rising. And you see this all over the place. We have some really beautiful ones in Mission Trails. This we also see, you can also see, porphyritic textures in intrusive rocks as well. Finally, a couple little samples. I'm going to just pop these up in front of my screen here because that's probably the best, is this one here, this glassy texture. Believe it or not, this one does not contain any minerals. Why does it not contain any minerals? Because it crystallized at very quickly. It didn't even have time to crystallize. It cooled so quickly. So it is technically has the same chemical structure as glass. Likewise, if you were to put a bunch of air into this, you'd have pumice. Now let's get things like this tuff, where you have little ashes that fall down and all weld together, preserving little air spaces. This one's actually kind of on the light side. You can also get air bubbles trapped like this piece of vesicular basalt that has lots of air trapped in it. These are all several examples of various other additional textures you sometimes find in igneous rock. Then finally, you can also get rocks that cool in columns like this. These columns, again, are generally formed. The rock hardens, but continues to cool at a few hundred degrees. As it cools, the solid rock begins to shrink. Generally, these columns are going to be perpendicular to whatever surface was in contact with the atmosphere. And these are special. They've been used as an installation piece. So that about wraps up what I've got to teach you about igneous rocks.